Hello and welcome to this video about diagonalizing matrices. This is the third step in this series, and I've decided to make a video especially about storing the eigenvalues. After the second step, you've probably made a list of unsorted eigenvalues equal to the dimension of the matrix. Now it can turn out that some of them may be equal, and this computer program has to be prepared to handle the worst case where they might all be equal. So now's the time to define two variable types used to store eigenvalues. The first type is called an eigenvalue list type. This contains two attributes, the first being equal to the number of eigenvalues found, and the second being a list of these eigenvalues. So here's an example of what I mean. There are 6 eigenvalues in this list, and there's an array of what these 6 eigenvalues are equal to. They're unsorted in the order that you found them as you searched for them using a polynomial root finding function. Here's another example. There are 3 eigenvalues, so e.number is equal to 3, and the 3 eigenvalues are listed below. And here's a third example. You can count these eigenvalues in the list and see that there are 4 of them. And so now to define the second eigenvalue storage type, called an eigenvalue frequency type. This contains 3 attributes. The first, called number, is equal to the number of different eigenvalues. The second, called values, is a list of these values. And the third, called occurrence, is equal to the number of times each of these eigenvalues occurs. So here's an example of the first type of storage containing the number of eigenvalues and a list of them. And here's how they'd be stored in a frequency type. Notice that because all of the eigenvalues are different, then they all occur only once. But in this example, we have 6 eigenvalues, and some are equal. There are 2 5s and 3 -7s. So if we put these in the frequency type, then we'd only have 3 different types of eigenvalue, with 5 occurring twice and -7 occurring 3 times. The placing in the array is important. Since the 5 is the first value listed, then its occurrence, which is 2, must be the first element of the occurrence list. So we say that the ordering is important. But it doesn't have to be sorted by size, but you can order it this way if you want to. So here's another example. In this list, 19 occurs 4 times, and so we have only 5 different eigenvalues, but most occur multiple times. And so here's another example. You can see that there are only 2 different values in the list, even though it has 11 values. And so this is how it is stored in an eigenvalue frequency list. 19 occurs 8 times. And so code has to be written to transform the eigenvalues being stored in the first type into the second type, so that the Eigen Vectors may be properly associated with them. And so now it's time to write the code. We firstly set a counter variable k to be set outside the main for loop. This is a counter for the position in the eigenvalue frequency list. So now we create the main loop that steps through all of the eigenvalues stored in the first list. We look at the particular value stored in the first list at position I. We're going to evaluate C to be the amount of times that this particular eigenvalue occurs in the entire first list. It's going to be incremented as we go through the rest of the list. We found it at least the first time, so it is set to 1 to start with. And so we'll loop through the rest of the list, and this starts at I plus 1. And so every time we find this particular eigenvalue again in the rest of the list, then we increment the counting variable. We close both loops at this point with 2 curly brackets. After we've traversed the rest of the list, we now have the amount that this eigenvalue occurs in the rest of the list, and we can copy these 2 values into the frequency list. And then we can increment the frequency counting variable to put the next value of an eigenvalue and its occurrence into this frequency list in the next position. And now we have to write code so as to remove this particular value from the rest of the first list, so we won't find it again, and so it won't end up in the frequency list a second time. This part can be combined in the loop to count all the occurrences of this eigenvalue, but I decided to put it into a second distinct loop for ease of explanation. And so I've decided to make a second pointer called L that follows the main pointer called J. It follows J in such a way so as to remove elements from the rest of the list, if they are equal to B. I've decided to make L equal to the length of the list when B is the last element in this list, because it won't enter the loop and has to be treated differently, because the length of both lists will be equated to it. And L is set equal to the next element if it enters the loop, so that it will follow J and lag 1 step behind every time it finds a value equal to B. So here's the main loop that will step through every value in the rest of the list. So when the next value is not equal to B, that is the value that we're trying to remove from this list, we do the following. And as we evaluate this expression, it acts so as to erase all other occurrences of B in this list. But this line is only executed when the value pointed to by J is unequal to B. We then increment the second pointer L, but only when the value isn't equal to B, so as to make it lag behind J 1 step for every occurrence of B in the rest of the list. And then the number of eigenvalues in the first list is lessened if there is more than one occurrence of this eigenvalue found, and this has to be copied into this first data type. And so here we can evaluate the number of different eigenvalues in the second list, and it is equal to the number in the first list, since all of the multiple occurrences of eigenvalues have been eliminated. So now we're in a position to expand the second data type to include eigenvectors. Usually if an eigenvalue is found n times, then it has n different eigenvectors, and we need to align these two. We could just place them in a matrix and have an index reference to which column it is in. But sometimes there aren't enough eigenvectors for a particular eigenvalue, and then we need generalized eigenvectors, and we need to treat this differently. But for now, if all of the eigenvectors can be found, then we can search them out and diagonalize the matrix. And this finishes our explanation of this code. I wish you good luck in your coding of this function. In the next part, we'll start to evaluate the eigenvectors.